This is lecture 26. So currently we are working with circuit simulation. So in the previous lecture, so 1 week ago, we have thought about how can we describe the circuit schematic. So when we have a certain circuit, then we need to specify it. So without just to fix the schematic, we can share the circuit schematic with our colleagues. The file format called netlist provides such kind of capability. In its role, it is quite similar with our previous files, like for example, vertex file and element file. So for device simulation, in the case of circuit simulation, we have netlist file format. So you remember that netlist contains actually description about each circuit element. So R1, C1, L1, V1. So we can specify many elements and their connectivity is first specified. So we can specify their connectivity. After that, depending on element type, we can specify different numbers, and for resistor, this number will be regarded as resistance, and capacitor, that will be considered as its capacitor. The previous lecture was just devoted to the description about the circuit. Then let's go to the circuit analysis. What is the governing equation of circuit analysis? So I can ask you the same question. Then what is the governing equation of our device analysis, for example? Then you can now answer that threefold diffusion equation. That is the governing equation for each device analysis. So quite similarly, so in the case of a circuit analysis, we can ask ourselves, what is the equation we have to solve? So the answer is really straightforward. So the answer is Kilov's current law. That is really the governing equation of every circuit analysis. You know that this red dot is called a circuit node, and for each circuit node, we can apply Kilov's current law. So it can have many branches. So branches means that here branches, here we have a node, and here we have circuit element and another element and another element. And you know that each element has terminal and terminal and terminal. Branch simply means that the connecting line which connects the circuit node and element terminal and element terminal and element terminal. Kilohop's current law simply means that if we make a sum of branch current with a unified directionality, then we have to have a vanishing sum. Okay, so let's say that this is I1, branch current 1, branch current 2, and branch current 3. Then Kiriov current law is realized as sum of I1, I2, and I3 should vanish. That is Kiriov's current law. The reason why this Kiriov current law is so fundamental in circuit analysis is actually this Kiriov's current law is an integrated form of total current density conservation. So you know that here we have this form. This is simply means that current conservation, and this is consistent with our Maxwell equation. And you know, when we integrate, make a volume integration of this current conservation law over certain volume, for example, in this case, nearby or over a volume covering this circuit node, then eventually we have this Kiriov current law. So Kiriov current law is actually just a different form of current conservation. So since current conservation is so fundamental in our physical world, so that's the reason why we are allowed it to just solve Kiriov current law to describe or to analyze our circuit. Okay. Now let's say that we are now talking about this quite a simple system. Then if we apply the Kiriov current law to this node, of course here we have a second node. However, this node is really special. So why it is special? This is the ground node, and ground node we have very important relation, which means that the node voltage equal to 0 by definition. It is actually the meaning of ground. So this becomes the reference for our voltage. So without any hesitation, we can say that at the ground node voltage equal to 0. So it has the priority, so we can apply voltage equal to 0 in this case. Of course, for this case, we have no such condition, so we have to apply our Kiriov current law. In this case, let's say that this is current through the branch connecting voltage source, and this is the current through the branch for R1. So we are, then of course we can say that by applying the Kiriov's current law, sum of I sub V and I sub R should be 0. You know that Kiriov current law is always right, so it's okay. But you know, natural question is, here we have two unknown variables, and we just have one single equation. Therefore, the number of equation provided and number of unknown variables are not matched at all. Then how can we introduce additional equation to make our system determined? So this is still undetermined system. So we need certain equations. How can we make a supplement to this Kiriov current law? You know that we have not applied the nature of our voltage source and resistor. So quite naturally, we can say we need to introduce two more equations, for one specifying the voltage source and another one specifying the resistor. That is quite straightforward. We are now talking about certain circuit having circuit elements. So Kiriov current law just say the node property. Node means that node is a place where different elements are interacting to others. However, its own inherent properties, voltage source, resistor, capacitor, is not specified yet. So we have to introduce those in this line and that line. So then let's do it together with me. Although that is quite simple, let's do it together. In this case, now we say that it has its magnitude is given by VA. Then what is it? Then here voltage source simply means that voltage difference between this positive node and negative node equal to V sub A, equal to V sub A. Then what is it? This positive one is connected to this red dot, so our node voltage minus ground voltage. However, you know that our ground voltage is identically 0, so we can say node voltage equal to V sub A. That is too simple. However, let's go to the second one. Now this R sub 1. In this case, we can apply Ohm's law. So V equal to I R. So let's do it together. So what is the voltage difference between them? This is V naught and you know, in this case V node equal V minus IR. Here I is an unknown variable, I sub R, and its resistance is given by R1 equal to 0. Now we can have this relation. So let's say that we have these three equations. Then can you solve our circuit, or can you analyze our circuit? Yes, we can. So after that, we can realize that there are three unknown variables. What is three unknown variables? So node voltage V node and branch current IV and IR. They are regarded as unknown variables. Then now we can collect them all. Then we have three unknown variables. After that, this is let's solve it together. By solving this equation, you can easily understand VA is just given as V node is given as VA, and from this information, now our V node becomes VA. So I sub R now becomes VA divided by R1. So VA divided by R1. Finally, by applying this Kiriov's current law, we can understand I sub V equal to minus I sub R. So minus VA divided by R1 is the solution vector for this system. Of course, I fully understand all of you can immediately understand the current I sub R becomes VA divided by R1. You can immediately understand this one. we don't have to actually solve this coupled system of equations. So this is a really trivial one. However, the reason why we are applying this tedious job to this trivial system is this is the general procedure. By applying the same procedure to more complicated system, even in the case of quite complicated system, we can get the solution. Okay, so we can get the solution even for quite complicated system with million transistors or billion transistors. And that is the real situation in electronic company. The electronics company, they daily or weekly perform the simulation circuit analysis with million or billion transistors in a simulation deck. So how they do that? So when they leave their office on Friday afternoon, they just start their champion job. Then during the weekend, the computer runs, and then they come back to their office on Monday morning. Then they have a certain information about their chip. Okay, so therefore, although this procedure is really trivial, now you understand how can you do that in general. So what was the key point? So in this case, you have to first apply Kiriov's current law to every node, and also you have to identify your branch currents as also another unknown variables. So this type of analysis is called as nodal analysis. So yes, so this is nodal analysis, the analysis based on the circuit node. That is the way of our analysis. Okay, of course, in reality, if you are working with the realistic situation, then you have to use modified nodal analysis. That is the standard way. So MNA is the one you have to consider. However, we will not talk about it right now. We can go to the next slide. That is exactly the same I have explained up to now. We have Kiriov's current law, supplemented by our element specific description. So for voltage source, for resistor, or for capacitor, we can anything depending on its property. Let's go to the implementation. So you can identify that solution vector is recognized as this one, IV, IR, V, know the output. So that is the way, and you can see that the order is slightly different, but that doesn't matter. Actually, it's up to you. So you can define any way, any reasonable way of arranging your unknown variables. Then when you just write it down, it looks like this. Then let's just read it together in English. So in the last line or in the last row, you can see that this is just read as IVA plus IR1 equal to 0. So what is it? This is actually Kiriov current law. Then the first law says that output voltage equal to 1.0. So what is it? It is because we have, yes, 1.0 volt for this amplitude, voltage amplitude. So we have this one. And this second line just says that I sub R1 minus 0.001 V out equal to 0. What is it? This means that I equal to so I equal to V divided by R. You are now looking at this relation. So this is Ohm's law, which is suitable for a resistor. You can easily understand. We have three equations, and these three equations can be easily mapped into a matrix form. We did it already for device analysis. So to us, it is quite easy and straightforward. So by solving this equation, this one is also in the form of AX equal to B. So by solving this equation, we can immediately get the solution. Then the remaining thing is just to interpret it. Oh, now output voltage equal to 1 volt and the resistor current will be 0.001 ampere. So 1 milliampere will flow through this resistor. So that is all for our analysis. Since we have spent our entire semester to the device simulation, so we can easily understand the similarity between the device simulation and circuit simulation. So they share their fundamental structure. So we can have the similarity. We are now talking about RC circuit. What is the difference? Yes, here we have capacitor. If we have, for example, a resistor, then I will say that this is still quite trivial. In this case, of course, if we have two resistors, then we will have two nodes, non-grounded node. Of course, here we have ground node, but ground node can be omitted because this is really ground. And here and there we have two nodes. Then we can apply 2 KCL and 3 equations for circuit elements: voltage source, resistor, and resistor. But that is really straightforward, and you can easily expand your previous knowledge to this RR circuit, to resistor circuit. So you can easily agree with my argument. Has when you go to this RC circuit, we have something new, something which has not been discussed yet. So capacitor, then what is the relation for capacitor current and capacitor voltage? This is simply given by the current flowing through this capacitor is given by its capacitance multiplied by time derivative of voltage across its two terminals. That is quite much different. So you know that in the case of a resistor, we can write down in this way. Of course, this is a resistor and this is a capacitor. You know, C or R can be regarded as constant. So the only difference is current is proportional to the voltage in the case of a resistor, and current is proportional to the time derivative of voltage across that circuit element. That is most important difference between resistor and capacitor. So now we have to think about how can we consider the time derivative. So previously, of course, we had time derivatives. Do you remember? When we talk about the continuity equation, we had to understand this one. So round n over round t. So partial derivative of our electron density at a given position is simply given by divergence of our flux, and we have negative sign because we have large divergence term. It means that our electrons are escaping from certain position. So if we have a large positive divergence, it means that we will have eventually loss of electrons after some time later. So this will be the form of our electron continuity equation. Continuity equation. However, we never seriously thought about round n over round t term up to now. What was the reason? Because we introduced a magic word like we now consider only steady state. Then when you say the steady state solution, from its definition, we can easily eliminate this any kind of time derivative terms. So that was the goal. Let's come back to our system. We will consider also steady state solution. Let's say, then what will happen to this guy? Then obviously in this case, if you say so, if this is a steady state, really it becomes 0 because this is a steady state. Then I becomes 0. Now it means that node 1, node in and node out are connected through our capacitor, but this one does not conduct at all. So since this current is 0, there is no current conduction. Therefore, this one should be also 0 ampere conduction. So in order to have 0 ampere conduction, of course, the voltage across this resistor should be 0. So V of out node will become 0 volt. So there is no difficulty to analyze our steady state solution. Yes, we can calculate the steady state solution. However, think about this RC circuit. So are you really interested with only for steady state solution? So can you live only with steady state solution for this RC circuit? No. The main reason you are working with this RC circuit is you wanted to use it as a filter. So sending certain information and get the output. Then depending on its frequency, if you send a low frequency signal, you will get certain low frequency response. And if you send a high frequency signal, then you will get the high frequency response. That is the goal. So you have to consider frequency dependent behavior. So in order to define any kind of a frequency related quantity, you have to perform the time-dependent simulation. So since the application of this system is really frequency dependent, so therefore we should be able to time-dependent analysis for this circuit. I think that can provide you sufficient motivation to eventually deal with how can we describe this relation. Then how can we describe this relation? You know, I is also an unknown variable. You can say, now, for example, this is, let's say that this is IC, then yes, this is in the list of unknown variables. Yes. However, you have no unknown variables like dV over dt. Oh, this is not a unknown variable. So more specifically, then this V over capacitor is simply given by in node voltage minus out node voltage. You can easily understand this is in node voltage and out node voltage, and voltage across this capacitor becomes V in minus V out. So time derivative is also given by, so dV in over dt minus dV out over dt. So that is not that difficult. But point is, none of them, this one or this one, this one or this one, they are not in the list of unknown variables. So now things becomes really clear. Our goal now becomes, how can we discretize or express our term like this in terms of, for example, V in or V out, or other quantities like capacitor current or resistor current or blah blah blah. We wanted to express our time derivative term, this one, in terms of other quantities inside our unknown variable list. So that is the key. How can you express these time derivative terms? And you know that. Let's go. Oh, here in this slide, I have just shown you how can you make the analytic solution, because I wanted to recommend you to make a one-to-one correspondence between your analytic solution and your numerical solution, so you will get good agreement for this simple system. So that's the reason why I just show you the analytic solution. But simply just to discuss about the qualitative analysis on it. So your goal is you just apply the voltage, certain time dependent voltage source. Then what you wanted to have is just to collect output voltage. You know, output voltage is simply given by, in this case, resistor current multiplied by your R1, so 2 mega ohm. So in this case, your output voltage can be regarded as just resistor current. Now our input output relation just becomes our in voltage and resistor current relation. So then what will happen? Think about this. If you have really high frequency, if your frequency is quite high, then what will happen? So in this case, this capacitor will have quite a small impedance. Its impedance nearly becomes almost zero. So in this case, what you will get is your applied voltage will be almost exactly copied to this output node, because this one has a so small impedance. So if you have a certain frequency, then that will be copied, and your IR will be just to become your input voltage divided by your 2 mega ohm. That will be one extreme case. If we go to really high frequency, then capacitor will give us almost vanishingly small impedance. So this one becomes just a resistive circuit. So let's go to our expression for I of t. Then let's assume that our frequency or angular frequency f and angular frequency omega becomes quite high. In that case, then what will happen? You can see that we have, now we assume that our input voltage has the signature of cosine omega t, and this is same thing, cosine omega t related one, and this one has sine omega t related one. So this is in phase, this one is in phase, and this is out of phase term. Then let's say that we have quite high frequency. So quite high frequency. Then what will happen? Here we have a coefficient, this coefficient and this coefficient. Here we have omega squared r squared c squared, and here we have omega squared r. It's a first order c. So in this limit we will have 1 over r. And how about this second coefficient? In this second coefficient, we have second order term for omega and first order term in omega. So if we go to very high frequency, this one becomes 0. So in this extreme case, then I over t will be given by 1 over r v naught cosine omega t. This is input voltage and this is output current. Oh yes, therefore we will have just all resistive circuit. Then let's go to the next part. If we have really low frequency, then what will happen? Now in the exactly same manner, now this capacitor contributes to almost quite high impedance. So compared with this one, compared with this high impedance of capacitance, so this one will become negligible. This one will become negligible. So now we have just a capacitive circuit, and our current will be simply given by I R resistor current. This is same with the capacitor current and resistor current. That will be just becomes a 5 picofarad times the in voltage over dt. That will be our extreme behavior in low frequency. And let's go to, of course this is a time dependent one. So if we just transform it certain frequency, then we will have the I at certain frequency component becomes 5 picofarad times, in this Fourier transformed case, this d over dt becomes just j omega, and v in its frequency domain component. That will be the relation between our terms. And of course this one is time dependent behavior, and this is frequency dependent behavior in the extreme of low frequency. Then let's go to this one once again. If we go to really low frequency, then what will happen to this guy? If we go to really low frequency, then this part becomes just 1, this part becomes 0. So the first term goes away, and the second term, what will happen? So in the second term we have, yes, here we have 1, and this is omega. Of course, when you go to low frequency, still this one entirely go to 0. However, compared with this first term, this one has much larger value, so it is reasonable to approximate it as I of t is approximated as just minus omega c v naught sine omega t. What is it? So this is simply obtained by when you insert v naught cosine omega t, then you will get such kind of expression for it. Now, if we just apply our 2 KCL and 3 equations for 3 circuit elements, we will get this information. That is not that difficult, but here we have a time dependent term. How can we express this time dependent term in terms of our 5 unknown variables? That will be the goal. Solution vector is regarded as, for example, current of our 3 circuit elements and node voltages. Then here we have a system matrix which really depends on the instantaneous value, the value itself at a given time. However, we have additional system matrix which is related with time derivative term of our solution variable. So that is important difference between our previous resistive circuit and our RC circuit. Second row simply read as IC1 plus, now say that IC1 and minus C and dVdt of input node plus C dV V out. Yes, this is nothing but the expression for capacitor current. Anyway, when we make a system matrix, now due to the presence of our capacitor, we have quite an annoying thing. Previously, we had no terms. There is nothing like this. However, if we introduce a capacitor, then now we have to consider this time dependent term. Once again, our main goal is express this term. Maybe you can ask me in a different way. Oh, why don't you just include these time dependent terms into our list of unknown variables? Instead of 5 unknowns, why don't you just solve 10 unknowns? 5 or 10, doesn't matter. So just to say they will become also unknown variable. Then my question is, okay, then how can we express your newly introduced unknown variables? That is exactly the same question with our current question. Anyhow, we have to express those terms. The point is, now we use an implicit method to express our time dependent term. You know that this is time derivative term. That term is expressed as just our unknown variable and our given vector. Oh, that is the key point to express our time derivative term. Of course, this given vector is not any arbitrary vector. So this given vector contains the previous value of our unknown variables. So you know that this time derivative, although that is the derivative with respect to time, but anyway this is derivatives. So how can we discretize derivatives? So we take 2 points and take the difference and take the independent variable. Yes, in this case, how can we describe the time derivative? We calculate the time difference and the difference of our unknown variables at these 2 time instances. So if this is the axis of time progress, then currently we are talking about our present time. Yes, we are now talking about this one. Then in order to calculate the time derivative, we have to take the past value of our unknown variable and take present value of our unknown variable and take the difference and divide it by the time difference. That is exactly done in this expression. You know that this is present value of our unknown variable and this is past value of our unknown variable, their difference. So their difference is corresponding to this one. That is divided by time difference, and this is the division by time difference and division by time difference. Let me show you. interesting example. For example, how about this? So please allow me 1 minute to do it. Okay. Okay. So let's say that I have 1 second. I have 1 second, and my signal is given by sine 2 pi t. So what is it? I have 1 hertz signal. So let's just plot it. T v. Then I will have these beautiful graphs. Then let me just make a dv over dt. Then how can we do that? dv over dt from 2 to 100 is given by, so how can you do that? v 2 to 100 minus 1 to 99, present point, past point, divided by time difference 0.01. Then let me just plot once again. T is second instance to the final one, and dv dt is second and 100, because I have not calculated the first one and left. Then let me just draw it. Oh, how does it look like? You expect 2 pi cosine omega t, and it looks like really 2 pi cosine omega t. Oh, good. Then let me just draw the real 2 pi omega t. So now I will just use blue color, and 2 pi and cosine 2 pi t is second 100. Then what will happen? Oh, they look quite similar, but you know that here we have, can you see it clearly? We can see a little difference. Then let me just repeat this one with much smaller number of our discretized equations. For example, let's say now t is given by just 20 positions, and v is given by and dv over dt is given by up to oh wow, now we have 21 20, and yes, plot, yes, 21. Now this one is discretized version of our dv over dt, and now I will just to draw the exact form of, or exact or expected form our 2 pi cosine omega t. Then how does it look like? Oh, you can see that now it becomes more clear that our discretized time derivative and the expected time derivative are different. So you can easily understand the difference that is related with the error of time discretization. Okay, so let me just wrap up today's lecture. Oh, sorry about my almost 5 minutes longer lecture. Today, we have introduced the principle of circuit analysis. That was KCL. KCL was supplemented by equations for each circuit element, and we can build the unknown variables, list of unknown variables, and introduce a system matrix that was quite similar with the one in the device analysis. And we have to think about time derivative, and I have just introduced backward Euler scheme, which takes the present value and past value and take the difference. So that becomes one crude but working approximation for time derivative term. Okay, so in our last lecture on Wednesday, we will finish treatment of time derivative terms and come back to the device simulation, and I will announce our final presentation. So that will be the last lecture. Let's wrap up today's lecture and see you Wednesday. Bye.